Imagine trying to power a fully loaded Boeing 747 jet from London to Tokyo, right? But you're using the lithium-ion batteries that are inside your smartphone.
Oh, wow. Yeah, that is a massive physics problem.
Exactly. I mean, by the time you loaded enough of those battery cells onto the aircraft to actually make the trip, the plane would be so incredibly heavy it would never even get off the tarmac.
Right, because energy density dictates literally everything in heavy transport.
Yeah. Trying to fly a commercial airplane on lithium-ion batteries is kind of like trying to power your whole house with a box of AAA batteries. It just doesn't scale.
It really doesn't. We have essentially engineered our entire global economy around the physical properties of things like crude oil derivatives,
Yeah.
jet fuel, marine diesel.
Because they're light but pack a huge punch.
Exactly. They pack a staggering amount of energy into a very small, very stable volume.
Yeah.
And to defossilize those industries, we need a replacement that mimics those exact properties, but without the carbon emission.
And that specific challenge is the mission of today's deep dive. We're looking at whether harvesting the crashing power of the ocean's waves could be, the ultimate shortcut to replacing fossil fuels.
And we're also looking at why some of the most remote, windswept corners of the globe might become the energy superpowers of tomorrow.
Which is fascinating. To do this, we are exploring a deeply detailed study titled Wave Power for E-Fuels and E-Chemicals Production, Technical Feasibility, Economic Viability, and Regional Opportunities.
And what makes this study so compelling is that the global conversation right now is almost entirely dominated by wind and solar power.
Right. We naturally look to the land.
Yeah, but this research looks out to the ocean. I mean, it's a largely untapped resource covering over 70% of the planet. And they actually run the complex modeling required to see if it makes economic and logistical sense for you, the listener, and the whole global supply chain.
So let's get right into the alternative the study proposes. Since we know giant batteries won't fly, literally, the researchers focus their modeling on e-fuels and e-chemicals.
So we're talking about things like e-ammonia, e-methanol, and synthetic methane.
Right, and since you, our listener, are probably already familiar with the basics of electrolysis, we know the basic concept. You split water to get green hydrogen, combine it with captured carbon or nitrogen, and synthesize a hydrocarbon fuel.
If we connect this to the bigger picture, the absolute brilliance of that process is that it creates a drop-in fuel.
Drop-in, meaning we don't have to change the engines.
Exactly. The logistics industry doesn't need to scrap every cargo ship, pipeline, and jet engine on Earth to transition to green energy. E-fuels just slide right into our existing global infrastructure.
But the massive catch, and there's always a catch, is that the scale is the friction point here. We aren't just talking about a standard laboratory electrolysis setup.
Oh no, not at all.
To synthesize e-ammonia or e-methanol on a level that can fuel global shipping, you are talking about industrial-scale water splitting and direct air capture, requiring continuous gigawatt-level power.
Astronomical amounts of cheap green electricity.
Right. And the places with the most ravenous appetites for these fuels-heavy industry and transport hubs in Europe or East Asian nations like Japan and South Korea, they physically lack the land to generate that much renewable energy domestically.
They're entirely land constrained. You simply cannot pave over half of Germany with solar panels just to synthesize jet fuel.
Which would be a wild sight, but yeah, totally impractical.
Right. And that geographical bottleneck is exactly what drove the researchers to shift their focus away from crowded land masses and look out to the ocean.
So they simulated the concept of off-grid energy hubs located in remote regions, specifically dedicated to synthesizing these e-fuels and entirely powered by wave energy.
Yeah.
Okay, let's unpack this. Because the ocean covers 70% of the planet, why have we been so fixated on squeezing solar panels onto crowded land when the ocean is right there?
Well, it's a completely valid point, but you have to look at the geographical reality. You can't put these hubs just anywhere.
Right. The ocean is a pretty harsh place.
Exactly. How do you actually run a sprawling chemical plant in the middle of the sea? The study specifically models point absorber wave energy converters, taking inspiration from a company called Core Power Ocean.
So how does that physical mechanism actually work out there in the water? Give us a visual.
Okay, so picture a central floating platform. That's the hub, and it's anchored securely to the seabed. This is where your electrolyzers and chemical synthesis equipment live.
Okay, got it. A floating factory.
Right. And surrounding that central hub is a vast cluster of these high-tech buoys, these point absorbers. And they aren't just bobbing randomly.
They're designed to catch the rhythm of the ocean, right?
Exactly. They are engineered to oscillate in mechanical resonance with the incoming waves. Inside the buoys, a pneumatic system converts that linear up and down motion into rotational energy, which drives internal generators.
Oh, wow. So they're literally just riding the waves to spin a generator.
Yeah, and then that electricity is fed continuously via underwater cables back to the central hub.
But putting high-tech mechanical buoys in the most violent oceans on Earth, I mean, salt water, severe storms, the constant mechanical pounding.
It's intense.
Building machines to survive that environment for 30 years has to carry a staggering capital cost compared to just, planting a solar panel in a quiet desert.
It really does. The capital expenditures are tremendously high, and the researchers don't shy away from that at all in the study.
But I'm guessing the energy payoff makes it worth looking into.
Exactly. You have
Yeah.
to balance that high cost against the incredible energy density of the ocean. To find the optimal locations, the researchers integrated decades of meteorological wave data and cross-referenced it with geopolitical stability indices.
Because you need immense wave power, but you also need a stable government to protect a multi-billion-dollar infrastructure investment.
Right, precisely. You don't want to build this in a volatile region.
Right.
So they narrowed it down to 3 specific geopolitically stable areas: the Southland region of New Zealand, the Magallanes region at the southern tip of Chile, and the waters off the coast of Ireland.
Now, Chile and New Zealand share a really distinct geographical advantage for this. They both sit deep in the southern hemisphere, right in the path of what sailors call the Roaring Forties.
Yeah, the Roaring Forties are legendary for a reason. If you look at a topographical globe from the bottom up, looking at Antarctica, there is virtually no landmass to interrupt the wind as it whips around the globe.
It just circles and circles, building up speed.
Right. Without continents to act as windbreaks, that wind transfers its kinetic energy into the ocean over thousands of unobstructed miles. Oceanographers call it an infinite fetch.
Infinite fetch. I love that term.
It's great, right? And by the time those swells hit southern Chile and New Zealand, they have transformed into monstrous, relentless waves.
And the study translates that relentless wave action into a metric called full load hours, which basically measures how often the equipment is running at maximum capacity.
Right, and the numbers are wild.
Here's where it gets really interesting. The simulation shows Chile and New Zealand seeing over 7,000 full load hours per year out of 8,760 hours in an entire year. That is profoundly consistent.
It's almost nonstop. And that consistency solves one of the single most expensive problems in renewable energy battery storage.
Because with solar or wind, you have to build colossal battery facilities to keep your chemical plant running when the sun goes down or the wind drops.
Exactly. And batteries are exceptionally expensive, not to mention they require intense mining of critical minerals.
Right.
But because the swells in the Roaring Forties almost never stop, the study found that wave power is so consistent, it cuts the need for batteries by 25% to 100%.
Wait, 100%? So no batteries at all?
Yeah. In the Chile and New Zealand simulations, they were actually able to run the chemical synthesis hubs with 0 battery storage. The wave energy basically acts like a continuous heartbeat for the facility.
That is incredible. But let's look at the harsh economic reality the researchers uncovered, because it's not all perfect. They ran an optimization model, the Energy Hub LUT model, to compare a pure wave-powered hub against a hybrid hub using onshore wind and solar panels.
And that model reveals a really tough reality for wave technology. On purely economic terms, on a cost per megawatt hour basis, onshore wind and solar still win.
Even with the cost of those massive battery banks we just talked about.
Even then, Chile produces the absolute lowest cost e-fuels overall using land-based renewables. For instance, producing e-ammonia in Chile with wind and solar costs about 51.1 euros per megawatt hour.
Okay, so what happens when they add wave power into the model?
When the model adds wave power into the mix, the overall cost of the fuel actually goes up slightly. That high capital expenditure for the wave converters, the CapEx, just makes it more expensive to build.
So what does this all mean? If onshore solar and wind are cheaper to build and operate and produce a cheaper final product, why bother with these giant wave buoys at all? Why did the researchers even run this incredibly complex simulation?
Well, here's the big aha moment from the study. It comes back to the spatial constraint we touched on earlier. The simulation doesn't just evaluate the economics, it evaluates physical limits.
Right, physical space.
Exactly. Take the Southland region of New Zealand as an example. The study found that if you wanted to meet just 39% of the e-fuel demand for Europe and East Asia using only onshore wind and solar generated in New Zealand, you would need to cover 254% of the entire Southland region's land area.
Wait, 254%. That means even if you paved over every single farm, forest, and town in the entire region with solar panels and wind turbines, you would still be less than halfway to your goal.
Yeah, it is physically impossible. You literally run out of land. And that reveals the true value proposition of wave power.
Ah,
It's not designed to undercut solar on a pure dollar-for-dollar basis today. Its value is that it does not compete for terrestrial land.
yeah.
It unlocks the massive empty expanse of the ocean.
That completely reorients the argument. It's not wave power versus solar power, it's wave power versus running out of usable planet.
Precisely.
But let's assume we do this. We build a sprawling offshore wave hub in Chile or New Zealand. We use the ocean to synthesize millions of tons of e-methanol or e-ammonia. We still have to transport that fuel to the industrial centers that actually need it.
Right, and the physical logistics of moving the energy is where the model gets incredibly nuanced. Shipping distances add significant costs. You have to factor in the fuel burned by the transport vessels, the capital cost of the ships, the export terminals, all of it.
And New Zealand and Chile are incredibly remote. I mean, they are between 14,000 and 22,000 kilometers away from major European demand centers, like Hamburg, for example.
Yeah, it's a massive journey. And this is exactly where Ireland suddenly steps into the spotlight in the study.
Right, because Ireland is only about 1,500 kilometers away from mainland Europe.
Exactly. And the study details how the physical state of the fuel being shipped completely alters the economics.
Tell us about that, because shipping liquid is different than shipping gas, right?
Completely different. If you are shipping a dense liquid fuel like e-methanol, a 22,000-kilometer journey from Chile only adds about 1 to 6% to the final cost. It's really not that bad.
But gaseous fuels are a completely different logistical challenge. If you synthesize something like e-methane, you have to transport it in specialized cryogenic ships.
Right. Liquid methane must be kept at minus 162 degrees Celsius.
That is unfathomably cold.
It is. And over a long, multi-week voyage from Chile to Europe, keeping that cargo cold means some of the gas inevitably vaporizes. It's a process called boil-off.
So you're literally losing your product as you ship it.
Exactly. That lost gas severely impacts the economics. For gaseous fuels, shipping from the southern hemisphere can add up to 13% to the final cost.
Which means Ireland's proximity completely reshuffles the economic deck here. Because the shipping route from Ireland is so short, it suddenly makes Ireland's slightly more expensive wave power highly competitive.
What's fascinating here is how the model shows that for certain fuels, once you factor in those cryogenic transport costs, the final delivered cost from Ireland is actually cheaper than importing it from New Zealand.
Wow. And beyond the raw economics, buying fuel from Ireland instead of halfway across the world is a significant victory for European energy sovereignty.
Absolutely. It keeps the supply chains short, secure, and resilient against any global shipping disruptions.
So to you listening, just like shipping costs dictate the price of the imported goods you buy online, global shipping distances will literally dictate the price of the green fuel powering our future global economy.
It really is all connected.
But there is a fascinating detour in this study that we definitely need to explore. The researchers took all this data regarding the unrelenting consistency of wave power, and they applied it to a completely different, highly contemporary problem.
Yeah, this was a massive plot twist. They ran an alternative scenario. Instead of using all that reliable wave power to synthesize chemical fuels, they modeled what would happen if you used it to directly power a 1-gigawatt data center located in New Zealand.
A 1-gigawatt data center is an astonishing amount of power. I mean, we started out trying to fuel airplanes, and we just found a massive cheat code for the AI energy crisis.
It really is. The connection to the current technology landscape is impossible to ignore. Right now, major tech companies, like Microsoft and others, are frantically searching for power to feed their new artificial intelligence data centers.
Because training large language models requires a constant, uninterrupted flow of electricity. You can't just pause a multi-million-dollar AI training run because a cloud passed over your solar array.
Exactly. It is an inflexible 247 baseload consumer, and that inflexibility exposes the vulnerability of standard wind and solar.
Right, because to guarantee constant supply for a data center using intermittent renewables, you have to overbuild your generation capacity and install gigantic battery banks.
Which drives costs straight through the roof. Tech companies are currently looking at reviving dormant nuclear reactors, and they're reportedly willing to pay over €100 per megawatt hour just to secure that baseload reliability.
And yet, the researchers found that because the ocean swells in New Zealand are so incredibly consistent, wave power acts almost like a mechanical flywheel that never stops spinning.
Right.
It provides that 247 baseload power, requiring just a small supplemental solar array and minimal batteries for only 29.3 euros per megawatt hour.
It proves that if flexibility is limited and direct electricity is needed right now, wave power is uniquely suited for it. Whether you are running a chemical synthesis plant or a massive silicon chip processing farm, if your demand cannot be interrupted, the high full load hours of wave energy become a profound cost optimization asset.
You essentially deliver pure, reliable electricity at a fraction of the cost of nuclear power.
Yeah, exactly.
So let's pull all of these threads together. What this deep dive illuminates is that wave power might not beat onshore solar and wind in a straight dollar-for-dollar spreadsheet calculation today.
Right, the CapEx is still high.
But the physical world is constrained by land and logistics. When the world runs out of empty land to place solar panels, or when we need unstoppable 2047 power without massive, expensive battery farms, wave energy is really the ocean's ace in the hole. It provides a solution that simply doesn't compete for terrestrial real estate.
It reinforces that the energy transition requires a deeply integrated approach. It is about matching the specific physical properties of a resource, whether it's the intense sun of the Chilean desert or the relentless kinetic energy of the roaring 40s, to the precise geographical and logistical needs of the global economy.
It's an incredible piece of analysis. Again, the study we explore today is titled Wave Power for E-Fuels and E-Chemicals Production: Technical Feasibility, Economic Viability, and Regional Opportunities.
But before we wrap up, there is one final lingering thought, straight from a limitation noted in the research, that we really should explore.
Yeah, this part really stood out to me. Tell them about the Kerguelen Islands.
So, there is a vital limitation the researchers explicitly noted in their methodology. When they ran their global optimization model, it identified one specific location as having the absolute highest wave energy potential on planet Earth, the Kerguelen Islands in the southern Indian Ocean.
And the data there showed an astonishing 8,000 full load hours.
Yes, over 8,000.
Yeah.
It is mathematically the most perfect location for this technology, yet the researchers actively excluded them from the final simulation.
So why exclude the most perfect location?
Because the Kerguelen Islands and their surrounding waters are a protected marine reserve. They are a World Heritage Site. It presents a very real dilemma for us. As the staggering energy demands of the global economy push us further off the land and deeper into the oceans, how will we reconcile the existential necessity to defossilize our heavy industries with the moral imperative to protect the pristine, untouched wilderness beneath the waves?
That is a profound question, and that is exactly the kind of tension that makes this energy transition so complex. We have to decarbonize the atmosphere, but we have to ensure we don't industrialize our most vulnerable ecosystems to do it.
That's a delicate balance.
It really is. Thank you for joining us today as we unpacked the engineering and the economics of the ocean. Keep questioning the obvious solutions, look for the hidden logistical realities, and keep diving deep.